In this part, we will introduce the peripherals that we find on microcontrollers and digital signal controllers in order to acquire these measurement or to control the inverters. So mainly the most common ones are digital input and output lines, which are used with pull-up resistors or pull-down resistance, but generally pull-up resistance. They can also admit some notification change on wake. We'll talk about this later. The analog to digital converters with different start-off converter sources with interruption. The digital to analog converter, which will output an analog voltage from the DSC. They are less common because generally the actions that we used are only digital, so we don't find them a lot in the control boards. We find them more in voice or speech synthesis or things like that. We find them more in speech synthesis. We have also timer and counter units with prescale, which timers that can be cascadable. For example, you can take 16 bits with 16 bits timer and cascade them and to produce a 32-bit counter. They are also used as watchdog, which prevents the system from being stuck in a loop and can be reset. We found also as peripherals, which, by the way, these are internal peripherals into the MCU in the microcontroller. This is internal to the MCU, but they are external to the CPU, Central Processing Unit. The pulse width modulation, PWM, it's the main system that will control the inverters, the choppers, which has a variable duty cycle. And it can also trigger the analog to digital converter start. We found also digital capture input lines to sense frequencies or echo. Real-time clock and calendar, less common. And then you have the communication interfaces. So the communication interfaces, we just see the serial peripheral interface, the SPI. The most common one is the serial communication interface, which is called also Uart. We can see them in more details, by the way. And the inter-integrated circuit, or I2C, I2C, which is very common for sensors. Another communication interface is the control area network, CAN bus, which is mainly used in automotive industry. Now also for Internet of Things communication, we are using USB, Ethernet, Wi-Fi, and Bluetooth. Nordic, it is a proprietary protocol, N24L01, very wide, it's 2.4 GHz, but it's a very wide range. It is used also in toys like Xbox remote controls. Zigbee, Z-Wave for home automation, but these ones requires like the USB and TCP/IP, the Bluetooth requires a hardware or software stack, which now we can find it embedded in the chip by itself. So let's begin with the digital input-output. I took an example of a low-line 32 microcontroller, which is an ESP32. So this is the ESP32. And here you have the connections. You have the USB, micro USB to program it. It has also a connection to a battery, a LiPo one-cell battery. And as you can see here, the digital input-output are called general purpose input-output. You can see 13, 0, 4, etc. Some of them, like these ones, can be put only in input, because for a digital input-output, you must first choose the direction, whether you are using it as an input or an output. So you have also, depending on the microcontroller, Is it its VDD, its voltage, is it 5 volts or 3.3 volts? And if you use it as an output, it cannot drive directly a motor. You need an amplifier because its output current is limited. Generally, it's limited like 4 milliamps. So if you want to just switch a LED, you need to put a resistor in order to limit the current to the maximum of the output of this microcontroller digital input-output port. For the use as input, it can be programmed with a pull-up or a pull-down resistors. So a pull-up resistance is a resistance that is connects this input to plus VDD. So when there is nothing, or it's in the air, the potential of the voltage of this input pin is linked to 3.3 volt. And then you, with a switch or what else, a push button, you can force it to 0. So you cannot have any floating voltage on these input pins. So this is very important if you don't want to bother yourself with putting external resistance. Some microcontrollers have these pull-up resistors inside the chip. Also, many of them have change notification interrupts, so you can interrupt the microcontroller and start an interruption or an interrupt service routine that can execute a certain code when there is a change on the this digital line. It can also wake up if you put this chip into sleep mode or idle mode. It can switch. It can wake up this microcontroller and it resumes its program. So this is for the digital input-output. We found also analog ones like this one, ADC1, 6, ADC1, 7, ADC2, 5. So this green one can be also used as an analog signal. We have here also DAC pins, which here you have DAC1 and DAC2, digital to analog converter pins. So what is ADC? ADC, in fact, and the DAC are systems that goes from the analog world to the digital world, or from the digital world to the analog world. So let's take, for example, a voice signal or an electrical signal that has this shape. So you filter it, you get off this high frequency component, and then you make some sampling. Okay, to sample the signal, we'll see it later, and then we convert it into numbers. You can, with this number, you can process them through a digital signal processor or microcontroller, and then you output them. You can convert them back from digital to analog. You filter, and then you output them on an amplifier for making a noise or making a sound. So the process of analog to digital converter is from this for example, analog signal, which is an amplitude versus time. And then you sample. What is sampling is using a sampling period, and at each period we will measure how is the voltage. So we'll take this point, and I say that my signal will not move, not change over one sampling period. And then the other sampling period, I will take a flash of or an image of the signal over this sampling period. And then I can weight all these voltage, okay, here, and I will weight them, as you can see here, for each sample time. I can weight this amplitude, and I can convert it to a number. So here you have 0, 0, as you can see here, you have 15, plus 60 plus 85, etc. And then you have also the negative values here, and these are produced by the ADC, and are outputted to be used by the microcontroller. So the characteristics of this ADC are the sampling time and the synchronization. If you want to use this ADC to measure two current for the motor, you can have two ADC working in parallel, or you can have two sampler, one on each output, and then you convert the first, and then you convert the second. So you take the image of these two currents at the same time using these samplers, but you convert them into these numbers, not synchronously, but no problem because your process is at very high speed. So this is the conversion time. The more accuracy you need, for example, 12-bit ADC or 16-bit ADC, 16-bit IDC takes more time than 12-bit ADC. Now that we have processed this current, we need to output a voltage to control the digital systems, inverters, choppers. So we need pulse width modulation. So there are dedicated PWM generator modules included in DSC and DSP boards. We need to configure them and we need to update duty cycle. So the ADC, the duty cycle you can go on this site if you want to have an animation of this. As you can see here, you have these PDCs that are moving. I can change them. Okay, this is a three-phase PWM working. So if you follow the red one, PDC1, you see you have very wide here, and then you have a narrow width. Okay, when the PDC goes up, so it's inverted. So when it goes up, you have here the duty cycle that is changing. And then you can also decrease the amplitude. So I leave you this website. You can see the animation, and also for space vector modulation. Okay, I give you an example of the synchronization, which is important. This is a three-phase PWM with an ISR, interrupt service routine execution time. We can see here in green. So when we begin the ISR, I will put this digital output to 1, and then when I finish, just before finishing the ISR execution, I put it down. So you can see here that the delta here is 4.8 microseconds. It's a vector control of machine with the current and speed control. And you can see here the synchronization with the PWM, phase A, phase B, phase C. And this is for 20 kilohertz PWM. I can show, for example, another example with the current. As you can see here, the current control with the PWM. It's 10 kilohertz one. Here we have some steps on the current. Let's show. Okay, let's continue with the communication interfaces. So we have the most common one, it's the Uart or the SCI, serial control interface. The universal asynchronous receiver transmission, Uart, is the most common name for microcontroller, and this is very old one. At logical level 0.5 volt or 0.3.3 volt, we call it Uart, and at industrial levels it is called RS232. It's the same one, there's just the levels that are inverted and amplified. So it's a full duplex. That means that you have the reception and the transmission that are on two separated lines, so you can talk when you are listening at the same time. And you have special buffers for the receiver and the transmission. Generally, it's an 8-bit data transmission with 1 or 2 stop bits. You have a parity check for data changes. You can also have some hardware control, TS and CTS, or you can use software flow control. It depends with an Autobot feature. this is very simple. There is no clock on it, but you cannot go very high speeds. So 192 kilovolts, it's a maximum one, let's say. If you want to go faster, you use the serial peripheral interface. We saw it earlier. It requires four connections. So what is called SDO, serial data output, it's called master output slave input, and SDI is master input slave output. So the slave will give data to the microcontroller, and here the master will give data to the slave, to the screen, or to the sensor. And then you have a serial clock that is imposed always by the master, and you have also a chip select that can be used with this or with an external digital output. So I'm not going into details, but just want you to know that these are very common. What you need is how to decode this information and how to code them, because this signal you can extract the variables. For example, for the thermocouple max 6675, you have libraries, and that gives you the information directly in terms of numbers representing the temperature. So you don't have to bother yourself with how to do the conversion, and you have the library. Arduino, you find a lot of Arduino libraries for a lot of sensors, so you better look for them. The SPI is mainly used for interfacing serial EEPROM, electrical erasable, programmable read-only memory, shift registers, OLED displays, analog-to-digital converters, DAC, etc. Another interface that is widely used is the I2C. It is also a synchronous transmission and reception, but it uses only one data line and one serial clock. So you have a master and many slaves, and each slave has an address that is transmitted on the SDA, and only the slave will listen to the address that corresponds to him, and he will answer back on the SDA. You can of course transmit command, you can receive the information. So this is an example with an OLED screen and an Arduino. So you need only 4 wires and 2 communication wires. So this is the power, this is the ground, and the 2 communication wires. The master starts the transmission by pulling the SDA low, issuing the start bit while the serial clock is still high, and then you transmit the 7 or 10 bits address. It depends on the type of protocol, and the read-write signal. Wait for the acknowledge, and then you can have the command, or you can get the data. It depends if you are writing or reading. So you can find more details in these links. The last one wire that I want to talk about is the CAN, so control area network. It's 2-wire also bus, and you have it's mainly used for automotive system. You can have many systems that are connected on this, and everyone has an address and can speak or filter by an address, a mask address. You need of course a CAN transceiver between these TTL level signals and these CAN bus where the voltage are more effective. So it's exactly the same. Not exactly the same, but it's same thing. You have the address, so you have 2 types here, for example, for the 11-bit identifier address, and then you have data. You have CRC, which is for code correction. So it's more reliable protocol. And what is interesting is that the system for many microcontrollers is independent of the CPU. So at the end, the information goes to a DMA canal directly to the RAM, and it will fire an interruption to tell that CPU that the information is ready to be read. So here is an example of testing line of between these two transceivers. So the line is here between these two, and I have two microcontrollers speaking on CAN bus to this and from one to this. This is for a BMS, battery management system protocol. I use the MAX3051 as a CAN transceiver for this project of 96 LiPo cells BMS and two DSP microchip microcontrollers.